Thanks. Okay, can you see my screen?
Yes, doctor.
Okay, so I'm sorry, this is incomplete because this is pi, but this is only u. So this is pi, but we don't have space here. So minus VE. So in general, what we're writing here is just u. I was checking. Okay. So in the next session, in the next minutes, we're going to explain that. So this is just u. Okay. Now, in this case, we're going to assume that the section of the element is uniform. So this dV, we're going to express it as a constant dx. Since this is constant, doesn't depend on x or L, or I'm sorry, x, y, or z, the integration will give you just the volume of the element. Okay, so I'm going to say that to duplicate that. Okay, since our bar element has uniform section, okay, the integration produces, so the u is going to be equal to 1/2 the displacement. This is a rho, and then the integration, let me go back. See here, it's going to be A, EA, and we're going to have an L. But we have L here and L there. So one of them will cancel and the other will survive. So we're going to say that that's equal to EA over L. And then from this vector, we're going to say that this is equal to minus 1, 1, minus 1, 1. Okay, so the integration is AL divided by L squared. So we cancel 1L. So that's what we have. And then on the right, we have this. So this is D transposed. There. And we do this and this, complete this operation, and that will give us, multiply this times that, that's 1. This times that is minus 1. In the second row, this time that is minus 1. And this time that is 1. And you can see that this is the stiffness matrix for the bar element. There. I'm sorry, this is not T. Where are we? This is not T, this is not transpose. There. Okay, so here is a 1/2. So this is a row, this is a 2/2, and this is a 2/1. Damn it, I say 1 and I write 2, come on. There. So this is 2/1. Okay, the result is going to be a scalar, which is u. Okay, but remember that what we need to do is we have to differentiate u with respect to D1 and D2. Why? Because this is an assumption. And what we're going to try to do is get the stationary value varying the values of the displacement of the two joints. That's the idea. Now, this is u. let's go now to V. Okay, let's to V. Now, for the potential energy of external forces, we could have a force which is a volume type force. Okay, and we can call it several ways. For example, we can say that this is in the local and this is a body. Remember, in this case, these forces, they do not depend on the contact. For example, the weight. We could have also surface forces. Okay, well, there are several ways that we can call it. For example, we can call it T. That's going to be in the X direction because this is just a bar. And finally, we can have only concentrated forces on the joints. Concentrated on the joints. Okay, for example, we can call it FIX there. So this is force per unit volume. This is force per unit area. It is just force. Okay, so let's call it PE. Okay, so in the case of volume forces, okay, so VE of the first type. Okay, so is equal to what? Equal to the product. Okay, for example, we have something like this, and here we have a D volume. So this force, for example, this is differential force, is going to be equal to this body force, which is force per unit volume times dV. So that's force, and this element will move in this direction. This is the local direction that we call it, for example, U is in the local direction. So this is the work, the potential work that could be developed by this little force. So that's that, and dV. And then we have to integrate on the whole volume. So this is force, differential force, body force, and multiplied by the displacement that will give us the potential work. Okay. Now, to do this, I could leave this, but this is not something that we like to do. Okay. What we can do is this. We can take the simplest case, which is equal to a constant, and remember that this, in our case, we're going to, let me go back. See, I need to express this in a similar way as this one. So on the left, okay, I have D transpose. So this U can be expressed as D transpose. So this is a row times the vector, and the vector is going to be 1 minus X over L, X over L. Okay, so we can take this out of the integration because it's just the values of the displacement at the joints. They don't change with the position inside the element. Now, let's consider as an example. Let's consider the case. So this is the body per unit volume, and let's call it like this one here. let's call it gamma. So that's the specific weight of the bar, or the material of the bar. And also, A, the sectional area, is constant. So we're working with a uniform bar. And let's see what do we obtain. Okay, so VE, so that's the potential energy of the first type of forces in this specific case, is going to be equal to what? We have D transpose, and then we have the integration. Now we have the integration of 1 minus x over L, x over L, and then we have A, or dA, dx. Okay, now, since there is no dependence on A, and A is a constant, what we're going to do is we can take this outside, I'm sorry, and we need a gamma. That's a force per unit volume. Okay, so we need to integrate that now. In order to simplify a little bit, let's define, to facilitate the integration. Okay, let's define this variable as x over L. Remember, this is non-dimensional. Okay, so dx, so we have dx here, is going to be equal to L dz. And the integration originally was from 0 to L, and we transformed that from 0 until 1. So let's do it. So if we integrate in y and z, there is no dependence on y and z, so we get the area, and that area doesn't change with x. Okay, so we can take that outside the integration. Also, we consider that this is uniform, so we can take that outside, and we are left with this. So VE, in this specific case, is going to be D transpose, and here we have gamma A. Gamma A, this is weight per unit length. We are going to integrate, instead of x, we're going to integrate in z. Okay, so we can say that this is equal to, from 0 to 1, it's going to be 1 minus x over L, by definition is z. And here we have z. And instead of dx, I have L dz there. Are you with me, people? Are you with me?
Yes, doctor.
Yes, doctor.
Okay, so Mr. Carreon, would you please integrate this term? And Miss Lopez, integrate this term. So we're going to have the result. We're going to have, you see, this is L A gamma. That's going to be the total weight of the bar, gamma AL. Then we're going to have this element there. And then we're going to have, remember, this is a row. We're going to have the two terms that Mr. Carrion and Ms. Lopez are going to give me. Carrion, do you have this term?
Yeah, z minus z squared over 2.
Yeah, but come on, this is an integration.
Oh.
Come on.
Yeah, it's 0.5.
1/2.
Because it's evaluated in 1.
Exactly, so it's 1. Ms. Lopez?
Yeah.
How did you get the integration of this, Ms. Lopez? Ms. Lopez?
Yeah, let me the same.
Say one half. So we're doing this, okay? Makes sense, right? We have this bar. So A is constant. Gamma is constant, okay? And we're going to do this. Instead of having this force, we're going to have two concentrated force, one here and one here. And how much is that going to be? W divided by 2, because this is W, and this W divided by 2. That's the result that we use in the homework, right? Homework 2. But now you can see that we can follow a procedure, a very consistent procedure. Right now, if I give you, for example, a distribution of A, you can take this inside and do the integration. Now, for example, if I can give you, we could consider, for example, instead of having uniform area, we could have a varying area. We do this integration. In this case, we need to express A as function of X, and we could do this conversion. So here, probably the force will be smaller than in this point. So how much? You have to do the integration. But we could follow the procedure. That's the idea, okay? So we have converted this distributed force into a discrete distribution of forces, two forces in the joints. Okay? Questions, people, questions.
Just doctor, I have a question about gamma is the...
It's a specific weight of the material.
Okay.
Okay, so it's force per unit volume, and it's weight per unit volume, really. So that's the most common body force, right? So the Earth is attracting the mass of this bar, and the force with which the Earth is attracting is the weight. So you don't need contact. You just feel the attraction. Okay, so that's the first one. Now let's do the second one. Okay. So now let's consider surface. In some cases, they call it traction forces. Okay, so let me draw horizontally. We have something like this, and we're going to consider a small area here. So we have something like this. Okay, so this is force per unit area. Okay, so we call it T, the traction. This is force per unit area. Okay, so in this case, so this is X local. So the force in the X direction is going to be what? This, that's force per unit area, times the length around this perimeter, the L, and times the X. Okay, usually what we do is we consider that it's uniform in the perimeter. Okay, so it's the same variation. What happens if we do not consider that? Well, in that case, what happens is that we're going to have a bending. If we pull more from this side than from this will bend. And we'll consider the simplest case. So usually we consider that Tx can depend on X, but usually we assume that doesn't depend on L. So if we assume that T is uniform in the perimeter, we can say that dF is simply T times L times dx. And this is force per unit length. So it's, let's call it F, little f, okay? F in the local. So this is force per unit length, time length, that's force. Now, so we can say that the potential energy of this second type of force has to be equal to what? Again, let me go back. Okay, we're going to do something similar to this one. We're going to take U, and for U, we're going to take this product, and then we're going to multiply by the differential force. So it's going to be equal to the vector D transpose, and then the integration over the surface of this thing. And then we're going to say that I have to put it back. So this is going to be U. That's that times 1 minus Z, X over L, jet, X over L. And then we have to put this. So it's going to be this times DL times dx. Now, since we're assuming that this is the case, okay, so this multiplication integrated will give us force per unit length, okay? So we have this vector, I'm sorry, this row. This is going to be L, the integration from 0 to 1, because we are going to convert the differential. And here, this is going to be force per unit area times dx. This is uniform. I'm sorry, I'm going to convert that the variable of integration. So instead of dx, I'm going to use dz times L. Now here, I also have one L. There. So let's check it. Okay, so this L here is from the integration, yes. This L here goes from X, and this is dx. Oh no, we don't need this one. Or do we? No, this is the one that we do not need. There. So this L, I put it outside. This dx give us that. There. We need an L here. So this is force per unit length times length, that's force. I'm in force per unit length, that's force. And that's non-dimensional. So we need another L somewhere. So this is the X there. So this is force per unit length. So that's, oh, we don't need this, the L in the denominator. Do we? So we have two forces. No, we don't need this in the denominator. I think we don't need this because here we have x over L and we replace it directly by this. This is that, right? So we don't need nothing in the denominator. This is the integration in L. This is force per unit area, and this is dx. That's there. Okay? Are you with me, people? Are you with me?
Yes, doctor.
Okay.
Yeah.
Let's try to do a simplest case to show you how this works. So this L times T, this means force per unit length, right? So I'm going to take this, but I'm not going to take it as a uniform. So let's take this to show you on a special case. So let's say to complete this exercise, let's take the following distribution of force. Okay, so let's suppose that we have a bar here, and let's suppose that we're going to take this variation. So this is x. So here, a very large value, and then we're going to be decreasing, and at the end we have 0. So this is going to be force per unit length. And let's take just one value of force divided by L. This gives us the correct units. And then we have 1 minus Z. Okay, so when Z is 0, we have the value of F or L, which is going to be the largest value. And when this is 1, we're going to have 0. So we have this linear variation. So we have to convert that into this problem. And as you can expect, in this joint, I'm going to put a value larger than in this one here. How much? That's our task. Okay, so let's replace this into this integration and let's see what do we obtain. Okay, so we said VE sub I is going to be equal to D transpose. We have L, this L, this L. This is force per unit length. So that's going to be, this constant is going to be outside. And then we integrate from 0 to L. And then we have 1 minus Z, Z, and multiply by 1 minus Z, which is this term here, and times dz. So this is completely non-dimensional. This is force, this is length, so that's correct. Let me go back just to check that everything is incorrect. So we have, this is expression, this is L dz. Yeah. Okay, so we cancel this. Remember, this is a scalar. We multiply this by that. Mr. Zamora? Mr. Zamora, would you please multiply this times that and integrate from, I'm sorry, this is not from 0 to 1. And Ms. Freire, would you please multiply this times that and integrate from 0 to 1, please? So let's see what they have to say. Because that's going to be equal to D times F, and then we have two values here. Mr. Zamora, would you please multiply this times that and integrate from 0 to 1?
Okay.
And Ms. Freire, please multiply this times that and integrate from 0 to 1. Give me the values, give me the results, give me the mic.
It's 1/6.
1/6.
1/3.
1/3. So what we're saying is that we have this, which is a linear variation of this force per unit length, and we're going to have 1/3 of that in here, and 1/6 of that into here. How much is this if I add 1/3 plus 1/6? 1/3 is 2/6 plus 1/6 is 3/6, that's 1/2. So adding, we're going to have F/2. And you see that that's the total force here. Because here I have F/L, so it's going to be F/L plus 0 divided by 2 times L. So that's S/2, which is the total force. Make sense? I guess so, right? So instead of this, we're going to have two forces here and there, but the total is the same. Let's take a second break here, and when we return, we're going to say a couple of words about the last case, which is the case where we have concentrated forces in the joints, and then we can put the whole thing together, okay? Then we have pi, the potential energy, and we can proceed in order to get the equilibrium through the differentiation. Okay, so let's stop recording.